Okay, so you are aware, on your final exam, I try to generally not put the most difficult questions on the final exam. Okay, I try to make sure that they are kind of moderate level, okay, of difficulty. Okay, the reason for that is the challenge with a final exam should not be how difficult I can make the questions, but on the volume of material covered by the unit exam. That's my philosophy. Not everybody agrees with me. I like to think of them as wrong. Okay, but that's how my test will work. Okay, so when you're looking at, a graphing question on the test, it's not going to be the hardest one I ever gave you. Okay, we've done some tricky ones. Okay, but I'm not going to put the hardest one. Does that mean there aren't going to be some questions that are challenging? No, there'll be some that are challenging. Okay, and that's because you have to know so much, right? But it's not because I thought up this great trick that makes this particular question so hard that only like 5% of people will get it right. I wouldn't do that on a final exam. I might do that on a quiz that we could use to review, but I wouldn't do it on the final exam. Okay, so just kind of know that going in. Other things about the final exam, just so that we're kind of covering all of them. Remember that you have to find a home for your phone, okay, that is not in your pocket before you go into the exam. You cannot have your phone or any other device that can connect to the outside world in there. Bring a snack, bottle of water, okay, something like that to get you through the test. Okay, remember that it starts at 1 o'clock on June 20th. You should be here at least by 1:45. Right? We usually open the doors to the gym about 15 minutes early just to get everybody seated and organized. Go in and find your test, find your row, find your test, okay, all that kind of stuff. So be here then. Don't be wandering into the school at 1:05. Okay, everything will have started. By the way, if you walk in at 1:30, your test is done at 3. Okay, your test is not done at 3:30. You don't get 2 hours from when you start. You get 2 hours from when the test starts, and that is 1 o'clock. If you are more than 1 hour late, you will be writing it in January. Okay? Because after 1 hour, people can leave the test and it is no longer secure. So you cannot begin writing it after 1 hour. Right? So please make sure that you are on time. It's less of a big deal in the afternoon. Okay? It's like a big deal when people forget to set their alarms for the morning tests. Okay? Don't be that person. The test is 2 hours. Okay, done at 3 o'clock. It should take you somewhere between an hour and a half and an hour and 40 minutes to complete well. All right, and that gives you some time to look it over. Right? If you're, you got to keep an eye on the time. Don't get stuck on one particular question. Right? If you don't know how to do a question after 30 seconds, move on to another question. Okay, don't let that one stop you from getting the questions you know how to do done. Right, so that's the thing I see happen most often on final exams. Somebody they'll sit and stare at a question for 15 minutes instead of doing the 5 questions they could have done in that time. Okay, you don't know how to do it after 30 seconds, move on. It'll still be there when you're done everything else. Okay. You have to stay in the test for 1 hour. Okay, after 1 hour, you can put your hand up and I'll come over because I'm supervising the exam, okay, and I will check to make sure that you have fully completed everything, you haven't missed anything, and then if at that point I will say, see you later, have a good summer, okay, and that'll be it. If you're done in less than an hour, you failed. And I'm not throwing down the gauntlet of challenge here, okay? I'm not saying like try to finish this thing in an hour, please don't, okay? I've been doing this for 25 years, okay? Nobody who has finished that test in less than an hour has actually finished that test, okay, and done a good job of it. I had one person finish in an hour and 1 minute, and they got 100%, but that guy was freaking brilliant, okay? And he's probably gonna work for NASA and send people to Mars one day, okay? That's like next level brilliant kind of guy. That's rare, okay? It takes more than an hour to do a good job of that test. So, don't be looking at, oh, I gotta get out of here, I wanna get out of here. Stay and do a good job, okay? 2 hours is lots of time for the test. I think that's it. Let's do physics. Oh, I remember what I was, okay. I got a video to show you because it's really funny, but I can't record it. Okay? What physics concept did that video deal with that we have dealt with a whole bunch of times? Which one's always dealt with pulling back on a bow and arrow or a slingshot or something like that? Oh, nobody remembers what kind of question that is? Work energy theorem. Okay, like I saw this video, and if I hadn't already finished your test, I was going to make a question about it because it's exactly the kind of question we did. Okay, so she pulls back on the slingshot. Okay, she does work. She exerts a force through a distance, and then she releases it, and all the elastic potential energy stored in the slingshot goes to the watermelon. The problem is when she released it, her fingers caught on the bottom part of the pocket, and it flipped over. So when it got to the other side, okay, the watermelon stretched the rubber band, conserving all the energy that she had put into it, okay, and then launched it back at her. Now, we could have calculated the speed at which the watermelon hits her face. And that's, like, it was a good-sized watermelon, too. Like, that had to hurt, and the sound was like, ooh, okay? But it's totally work energy theorem, conservation of energy. It's all that stuff that we did in class, okay? All right. It was a fail, but it was good, okay? All right, so first thing we went over, types of energy. That's going to be in the multiple choice. Okay, and that's the things like on your unit exam, I think there was a question about like there was a tank of propane. What kind of energy does the propane possess? And it was chemical energy, okay? Or you could have a ball rolling down a hill. That could be mechanical energy, or it could be kinetic energy, okay? So questions like that, being able to identify what energy type is most involved in a particular situation. And it's also important for work energy theorem questions. Being able to identify, is potential energy changing in this question? Or is kinetic energy changing in this question? Okay, those kind of things. So there's that on there for sure. It was the first thing we went over. Okay, so just general recognition. Then we went over thermodynamics. Okay, the first two laws. Okay, so the first law and the second law. The first law is, of course, the law of conservation of energy. Okay, and the second law tells us that energy always flows from high to low or hot to cold. Okay. Now, these will be, again, mostly multiple choice, kind of situational type of questions. And make sure you understand, how heat pumps and heat engines, what they are, okay? Because there could be multiple choice questions about that. Because that's, using the second law of thermodynamics or going around the second law of thermodynamics. So make sure you understand those. Second law also applies in Unit 4, obviously. When we're talking about energy transfers on Earth, it's going from the hottest parts of the Earth to the coldest, or design something that can keep food cold on a hot sunny day. Okay, that's again second law. Okay, the conduction, convection, and radiation part's not part of this unit, but we talked about the laws of thermodynamics at least a little bit here. Okay. Also included in this would be the difference between heat and work. Okay, heat and work are both transfers of energy. Okay, heat is a transfer or a change in thermal energy. Work is a transfer or a change of mechanical energy. Okay, so making sure that we keep those two straight. Could be multiple choice questions, checking your understanding of that. Okay, so heat engines, jet engines, the heat engine, heat pumps, fridge, air conditioner. Okay, the next thing we went on to, okay, were scalars and vectors. Okay, scalar and vector quantities. So make sure you know which ones are which. Okay. Maybe let's quickly list them right now. What are the scalar quantities we went over? Speed. What do we, distance. What else do we use to get speed? Distance and time. Time is scalar. Okay. The other two are a little trickier. Work and energy are also scalar quantities. Okay, so distance, speed, time, work, and energy, all scalar quantities. Okay, our vector quantities were velocity, displacement, acceleration, one more, force. Okay, those are our vector quantities. Now, why is it important to know those? I could easily put a multiple choice question, which of the following is not a scalar quantity, okay, or something along those lines. But more importantly, I give you an acceleration problem, you know, about a ball rolling down a hill, and I ask you to calculate the final velocity, and you do it all right, and you forget to write downhill on your answer, because it was a vector quantity that required. Don't get burned on that twice, okay? Like, fool me once, shame on you. Fool me twice, okay? I don't want to fool you twice. I don't have that many tricks in the bag, so, okay? So definitely know that. The first formula we dealt with in terms of scalars and vectors was V equals D over T. Okay? Now, there are no 5-mark V equals D over T problems on your final exam. Okay? We're past that. But there could be a simple V equals D over T calculation as a multiple choice problem. Okay? That would be a legitimate multiple choice question. Or you do have to use this formula with your graphing. Okay, as part of both position and velocity versus time graphs, this formula can come into play. Now, when we're calculating velocity, specifically with graphs, okay, there was a way we could alter this formula. What was the way we could change the top of it? Close. Final, not distance, but final starts with P. Position, yeah. Final position minus initial position, that calculates displacement. Okay? If I know those things, I just have to do that over time. That gets me velocity as well. Okay? If you have an irregular position versus time graph, that's probably what you would end up using. Okay, so just little things like that. That's where you're going to see V equals D over T for the most part. Okay, and then I think I wrote, yeah, D equals, all that stuff is on your formula sheet. You know where it is, because you've been, and you're going to get the same one. I actually just photocopied them yesterday. They turned out great. Okay. All right, acceleration was the next thing. Right, and this was what we just talked about. Here's why you need to know which things are vector and scalar. I give you an acceleration problem, and you got to solve for velocity. Okay? You could easily get a written response acceleration problem, okay, on your final exam, and definitely a simple one in the multiple choice. Okay, so as I said, yeah, written response problem. Now, after we did V equals D over T, and we did acceleration, A equals VF minus VI over T, then we moved on to graphing. Okay, there is a significant amount of graphing on your final exam. Some of the graphing will involve calculations, and some of it will simply involve reading and interpreting. Okay, you could very likely get a question where I give you a graph and I say, what is happening in the, describe the motion in the first part of this graph. Describe the motion in the second part of the graph. Okay? I don't even ask you to do any math. I just ask you to interpret what's going on in the graph. So you tell me, well, in part A, the object is accelerating in a forward direction, or in part B, the object is not moving, or in part C, it's traveling at a constant velocity in a forward direction. Those would be the kinds of things I could easily ask, even in the written response, okay, as opposed to in the multiple choice. Okay. Are there going to be calculations? Yes. Could it be y equals mx plus b? Yes. Okay. Could it be an irregular graph? Yes. Okay. All of those things are game, okay, and I'm not going to spoil which one it is. I want you to study them all, okay, but definitely know both types of graphs, position versus time and velocity versus time, are on the test. Okay. Okay, so in y equals mx plus b, you could be asked to extrapolate. That means calculate something beyond the graph. So I give you a position versus time graph that only goes to 10 seconds, and then I say, calculate the position of the object at 1 minute. Well, that's beyond the end of the graph, and you'd have to use y equals mx plus b to do that. Or I ask you, how long would it take to reach a position of 200 meters, which we'll say is beyond the graph. Okay, you'd have to go use y equals mx plus b. Okay, everybody all right with that? Okay, so how will you know if I give you a graph that I want you to use y equals mx plus b? If the equation is on it, I want you to use it. If I say, using your graph and the equation given, I want you to use it. Okay? I'm just saying that because we ran into that problem a little bit on the unit exam where I said exactly that, but people did something else. Okay? If the question says, do a question this way, you need to do it that way. I'm trying to test a certain thing, and I've probably set it up so you won't get the right answer if you do it a different way. Okay, that's what happened on the unit exam. Now, you guys in class, graphing was something that gave us a bit of trouble, but then, man, like you picked it up and you had it all figured out for the unit exam generally. That's good. You're definitely going to be tested on the same kinds of things. Okay, what you had to do on your labs, that's what I'm going to ask you to do here. All right, so if I have a position versus time graph, all right, let's say one of these ones here. If I have this position versus time graph, and let's just say that that last part is flat, okay? If I asked you to calculate the average velocity over the whole trip, how would you do it? Okay, well that is something I could definitely ask. Okay, so if that's a position versus time graph, can I read where the object is at any point in time on the graph? Okay, so does that mean I could probably find its final position and initial position? Yeah, this would be its final position, this would be its initial position, okay, and I would know the length of time the graph runs for. I could calculate the average velocity by going final position minus initial position divided by time. Do I have to memorize that that's the way to do it? Or did I just talk myself through it? Okay? It's way better to talk yourself through it than to memorize it, because like in period 1 I had this happen. I showed them this graph and right away I said, so how would you calculate the displacement? They're like, the shapes. Like, that's memorizing. You memorize that shapes get you displacement. They don't on this graph. Okay? It's a different graph. Right? So on this graph, I have position. I have a formula that has position in it. It calculates displacement. This formula calculates velocity using displacement. Oh, I can put them together. Okay? I just walk myself through it. What do I have? What can I use? Okay? That kind of thing. Now, on this graph here, if I asked you to calculate the total distance traveled, how would we do that? Like I can't just go final position minus initial position here, can I? Distance is scalar.
Each part of the graph, I just add position.
Exactly. I've got to do final position minus initial position, but I've got to do it for every part of the graph because distance is scalar and it's always getting bigger. I have to include this part where I went backwards, okay, where I didn't really include that when I calculated the total displacement. Okay? So as long as you understand what each thing is, the way to calculate it kind of becomes clear when you start talking yourself through the graph. Okay? if I have this position versus time graph, and I give you the equation, let's just say I wrote it like this. What would the velocity on that graph be? This would only be a 1-mark question, by the way.
It's 2.5.
2.5 meters per second. Okay, now do I need to memorize that the slope of a position versus time graph represents velocity? I don't, because I can figure it out. Okay, I can look at my graph and say, all right, I have position on the y and I have time on the x. If I solve for slope, and I'm doing this, y is my final position, b is my initial position. And if I divide that by x, I've just calculated displacement and divided it by time. The slope must represent velocity in this case. Okay, I don't have to memorize it, I just have to work it out. Okay. All right, here's another one I might give you. What's the acceleration of the object right here on that section of the graph? 0. Okay, how do I know that besides the fact that there were no numbers and it would have been impossible to calculate anything?
Because it's moving at a constant velocity.
Right, it's moving at a constant velocity there, okay? And that's not something we have to memorize, that's something that's like, okay, every time interval, it goes the same distance. Something accelerating would go further every time interval, okay? It would be curved. That's not curved, it's straight, okay? Now, if a question is out of 1 mark, is it a bit of a giveaway? Okay, remember that, it's important. I have to put, to be fair, I have to put the point values on a question. Okay, if there's only 1 point, there isn't anything to do except recognize the answer is there. Okay. All right, then we got velocity versus time graphs. Okay, oh sorry, that's, if you want to write that down, that's what we were just talking about, displacement and then distance. Okay, that's kind of memorize-y, but okay, that's what we did. Okay, so on our velocity versus time graphs, okay, we're going to have calculations to do there or interpretation to do there. So on our velocity versus time graphs, we could get a linear one, right? Or we could get an irregular one. Okay. If I asked you to calculate the acceleration on this graph here, okay, on the left, this was my initial position, or sorry, this was the start and this was the end. Okay, it's not position because it's velocity. Okay, could I calculate the acceleration over the whole trip for that graph? Okay, am I using y equals mx plus b for that? Not on this graph. There is no y equals mx plus b on this graph. It's irregular. Okay, do I have a formula that calculates acceleration? Yeah, this one right here, right? Could I use that? Yeah. Here's the final velocity right here. Here's the initial velocity times on the x-axis. I could totally calculate the acceleration. Okay? Again, that's not me memorizing how to do it. That's me walking myself through it. What if I wanted to calculate the total displacement? Okay. Does this formula here calculate displacement? I can get those numbers from the graph. Time is on the x-axis, so I always have access to that. Okay, and average velocity, I can get that. Okay, for this part here, it's traveling at a constant velocity, so I would just have to read the number off the graph and go base times height. Okay, for here, I'd have a little rectangle and a little triangle. Okay, during the triangular part, the velocity is changing, so the average velocity would be halfway between the bottom and the top, or the height divided by 2. Okay, and then I'd have that little box underneath that represents how far it would go if it traveled at the initial velocity. All right, ringing a bell? All things I might ask you to do. Okay, if you had this graph, would you still do the same thing? You would, yeah. You'd have this triangle where it's accelerating and this rectangle that represents how far it would have gone at the initial velocity. Okay. if I asked you for the acceleration on that graph, what part of the equation would it be? It would be m. It would be the slope. Okay? Same reasoning as before. If I solve for m, y minus b over x, y is a velocity. It's the final velocity. B is the initial velocity. Okay? And x is the total time. This is vf minus vi over t. Okay? It's just taking into account all the points and averaging them out. Right? So the slope could be the acceleration there. Would that, how many marks would that question be out of? If I gave you that graph and said, what's the acceleration? 1 mark. Answer's right there. Okay? Requires no calculation. Okay. Making some sense? Ringing a bell? Right. We just talked about all of that stuff. Okay, this is a velocity versus time graph. That's a 7, that's a 3, that's a 2, that's a 10. Okay, they kind of go like this. Okay, just that's where the 7 goes to. Calculate the total displacement of that object. Give you a minute. Okay, so in the first part here, we have an object traveling at a constant velocity of 3 meters per second for 2 seconds. 3 times 2 is 6 meters. Okay? Then we actually have this other section here that would represent how far it would go if it continued at 3 meters per second. Okay? So for another 8 seconds, well, 3 times 8 is another 24 meters. And then we would have, oh, well, that makes it pretty difficult to do, doesn't it? I erased something here that should have still been here. 4 seconds. Yeah, I don't know how you did this without that. Okay, so we got a 2-second base and a 4-second height. Okay, 4 times 2 is 8, divided by 2 is 4 meters here. And then this goes, it's 4 high and it runs for 6 seconds. Okay, that's another 24 meters. Okay, so we got 48, 52, and 6 is 58 meters. Okay, sorry guys, there was no way for you to do that. And nobody said anything. All right, does that make sense? Obviously on a final exam, I would make sure all the necessary numbers were there and that you could read them. Okay. All right, moving on here, work energy theorem. So the watermelon to the face concept. Okay, you'll never forget it now. You need to know, or you need to have an understanding of work enough that you could identify when work is occurring. Okay? Work is a change or a transfer of mechanical energy. Okay? Problem solving wise, we dealt with situations where either the kinetic energy of the object changed or the potential energy of the object changed. How could we tell the difference? In a question where potential energy changed, what would the object be doing? Be going higher, right? It'd be lifting. There'd be a change in height if there's a change in potential energy. If there's a change in kinetic energy, then we're looking at a change in speed. Okay? So if something is accelerating, that's a change in kinetic energy. If something is being lifted, that's a change in its gravitational potential energy. Okay, so there's some understanding questions, okay, in the multiple choice, and then obviously there's problem solving in the written, okay, where you'll have to go work is force times distance, and force times distance is a change in either kinetic or potential energy. Okay, you guys did really well on those, okay, on the unit exam, so that's something you'd want to continue because there's definitely at least one question in the written response on that. Okay, so if we are dealing with a kinetic energy situation, then we would have force times distance is the final kinetic minus the initial kinetic. If we were dealing with a work energy theorem on change in potential, it would be final potential minus initial potential. Okay, remember those are our formulas for the two types of energy. Okay, and then you would manipulate and solve, okay, for whatever part you were missing. Okay, you guys did lots of those and you were really good at them. Okay. And then we had law of conservation of energy problems, the EI equals EF, roller coasters, kids going down hills on sleds, okay? Even the soapbox derby race that went on last weekend, it was last weekend, okay? That would be, well, if it was truly a conservation of energy question, it would have been a lot more interesting because those carts would have gone a lot faster, okay? So, conservation of mechanical energy, initial energy equals final energy. Okay? The energy is not changing in these questions. Well, at least the overall mechanical energy is not changing. How on the exam would you tell the difference between a work energy theorem question and a conservation of energy question?
If it mentions both speed and height.
Yeah, if a question gives you both speed and height, it's got to be a conservation of energy question. We haven't done any work energy theorem problems that involve a change in both. Okay, you will in physics 20, but not here. Okay, another thing that a work energy theorem question will always give you, but a conservation of energy question won't, work or force. Those will always be in a work energy theorem question. They will never be in a conservation of energy question, because if they're present, energy is not conserved, it's being changed. So in a conservation of energy question, all that's happening is gravity is turning potential energy into kinetic energy. Something is going down a hill, okay? Something like that. Everybody with me there? Okay. Okay, so remember we can expand that out. Remember that mechanical energy is the sum of an object's potential plus kinetic energy, and that's what we're saying there, right? We would be saying potential energy initial, whoop, not equals, plus kinetic energy initial equals potential energy final plus kinetic energy final. Okay, remember we just keep expanding it out as we go. Okay, let's see how much we remember. Okay, we got a 20 kilogram object. Sorry, I'm not going to put 20 in there twice. 25 meters above the bottom of a hill, moving at 4 meters per second. Okay, a little while later, it is moving at 10 meters per second. Find the height it's at now. Give you a few minutes on that one. All right, so we know it's an initial energy equals final energy question. Okay, so that's going to mean initial potential plus initial kinetic equals final potential plus final kinetic. Okay, what I'm looking for is the final height. That's part of this, so I'm going to isolate it right now and say my initial potential plus my initial kinetic minus my final potential, my final kinetic equals my final potential. Okay, then I can plug in my formulas, m times g times h initial plus 1/2 mv initial squared, okay, minus 1/2 mv final squared equals m times g times h final, right? M's are going to cancel out, even though I was given the mass, I don't need it. Then I divide both sides by g, and I'm looking for h final there, so that's going to be 9.81 times 25 plus 1/2 times 4 squared minus 1/2 times 10 squared divided by 9.81. Okay, and then divide that by 9.81, and we're looking at 20.7 meters, okay, which makes sense, it's lower. Okay, and it should be lower. It's going faster. It's converted some of its potential into kinetic. Okay, ringing a bell? You guys did pretty good on that question on the test. So. All right, and then the last thing we talked about was efficiency. Okay, and that is simply, okay, that your actual work divided by your input work, okay, or how much energy you had to put in to do it, okay, gives you your efficiency as a decimal or a percentage. Okay, and that formula is also obviously on your formula sheet. Hey, anything you guys would like to go over?
Can we just see an efficiency question?
An efficiency question? Sure. Okay. Okay, that could be a pretty typical efficiency problem. Okay, so you got an electric motor running at 92% efficiency, supplied with 6,000 joules of input energy. How much work will it actually do? Okay. Yep. All right, give you a minute or two on that one, guys. Oop, I wasn't talking. Okay, so we can try this one. Okay, if you guys have other questions, just ask. Okay, I would rather you guys drive the bus than me. Okay, so if you have specific questions, please ask them. Otherwise, I'll just throw some examples up here that you guys can try. Okay, so the height of this triangle is going to be 26.51 meters. Well, now that I know the height of the triangle and I know the base, I can do the calculation there. Okay, so I'll take my 26.51, multiply it by 11, and then divide by 2. Okay, and I've got that section being 145.8 meters, and then I just add the two together. All right, so 212 meters in total. Okay, everybody all right with that? All right. For 3, if I want to calculate the velocity after 30 seconds, okay, y equals 2.41 times 30 seconds plus 6.04. Okay, I'm just solving for a y value when given an x. And then the opposite is true for 4. Okay, it would be x equals 100 minus 6.04 divided by 2.41. Okay, that would give me my time. Everybody okay with those? All right. Give that one a try. We'll go over it when I get back. Guess I better stop recording. All right, so in this one here, what force is used? So we're looking for the force. Okay, we're told the distance. And we're told that they want to throw it to a height of 21 meters. So that would be the final height. What can we assume is the initial height? 0. Okay, so if I know that information, okay, and I know that it's about height, then it must be changing the potential energy. So that would be force times distance equals potential energy final minus potential energy initial, which, since my initial height is 0, my initial potential is 0. So I can cancel it. It's gone. And I'll have force times distance equals m times g times h final. I'm looking for force. Divide both sides by d. Okay, and plug in the numbers. So we would have 1.5 kilograms, I think. Right. 1.5 times 9.81 times 21. Okay, and then divide that by the distance, which was 1.5 meters. Okay, so we need 206 newtons worth of force to throw that. Okay, everybody all right with that one? Okay. Anything else you guys in particular would like to work on? Otherwise, I can just keep throwing other questions up here. Okay, another work energy theorem question, or you want to do something else? Precipitates. What do we have that on there for? Okay, try that one. That's a different kind of question. I'll get better yet. Okay, questions on that one? So just an acceleration question. Okay, anything else you guys want to try? I'm sure I have other things on here. We did an efficiency question already. I guess I don't have that much other stuff. All right, well, we didn't do that one. Let's give that one a try. Work energy theorem question, but this time what kind of energy is changing? Kinetic, yeah, speed's changing, right? All right, so final speed of the car, okay, is what we're looking for, right? And we're also told that it starts from rest, which makes the question a lot easier because what's its initial kinetic energy then? 0. Okay, so when we say work is a change in kinetic energy, we can go kinetic energy final, and that's it. We don't have to write minus initial. We already know the initial is 0, and that saves us a bit of work. That's one of those kind of questions that, like, it's a moderate level of difficulty. Okay, if I wanted to make that question harder, I'd have given you an initial velocity that wasn't 0. Okay, so what am I going to do on an exam? Probably more like this. Okay, moderate level shows me you can do work energy theorem as opposed to you can do the hardest one I did. Okay, all right. So we've got force times distance equals EK final. So that means force times distance equals 1/2 mvf squared. We divide both sides by half of m, and then we square root to get vf. Okay, so we got the square root of 500 newtons times 15 meters. Divided by 1/2 times 1,000. Oh, that's silly. Okay. Half of 1,000 is 500, yeah? 500 times 15 divided by 500. The square root of 15. Okay, because the 500 is going to cancel here. All right, so square root of 15 will shortcut it. All right, so 3.9 meters per second be what we're looking at there. Okay, tomorrow, unit exam. Okay, I will let you write a little bit past the end of class. Okay, I'm giving my morning guys an extra 20. I'll give you an extra 20. Okay, just if you need it. Okay, and yeah, make sure you've got what you need. Okay. All right, good job today, guys.